If it's hard to see, you might want to move forward. That's a bit small.
That's the whole talk.
No. There are several of those. But I'm talking at the board, and that's kind of a reference. Shall I start?
Okay, so we're happy to have Professor Leila Schneps to tell us about relations between Grothendieck-Teichmueller theory and multiple zeta values.
So you're my guinea pigs for this talk. I've never given this talk before because usually, where's the chalk? Oh yeah. Usually I give a very simplified version of this talk. That's what I was about to say. But the reason I'm not doing it today, so I decided to be rather ambitious, is because there have been lots of talks by Deligny on multiple zeta values already, and there have been talks by Fudushou, and there have been lots of talks already. So many of the things I'm going to say would have already been heard. So I decided to try and cover something quite big. So this is the structure of my talk. Grothendieck-Teichmueller theory. I'd like to just give you a quarter of an hour description of what the whole theory is really about, where it comes from and what it's about. And then the theory of multiple zeta values. Now this, I'll stay on very simple because there have been quite a few talks here about this. And you can get into the theory. It's a nice theory because you can get into it very quickly with a minimum of information. But the connections between them, this is something that's explored by very few people, actually. And there's a huge connection, which is very surprising. To me, a very surprising and miraculous thing, because this theory is all about the absolute Galois group and the geometry of moduli spaces of curves. This is about zeta values, real numbers which are zeta values. And the connection between them is far from obvious. So what I'm going to do is, I'm going to talk about the connections. The connections are far from obvious, but when you start looking and when you see all the results that have been proved recently, these connections are very numerous and very deep, and there's something very important going on. And connections Grothendieck-Teichmueller and multi-zeta. 4 is going to be connections really between the absolute Galois group, which is the object at the heart of all of Grothendieck-Teichmueller theory, even though Grothendieck-Teichmueller theory essentially deals with the Grothendieck-Teichmueller group and geometry, the object at the heart of it is an attempt to understand this one. So how is this group contained with multi-zeta values? I'm not sure I'll ever get to part 5. I might not. But if I do, there has been a theory completely developed which all of these connections are things that have been observed, and some parts of them have then subsequently been proved. This is an effort to really make a theory which explains the connections in a completely coherent way. Mixtate, let's say, over Z. This is a theorem which has been developed by various people, essentially Goncharov, and with Beilinson and many other results feeding into his theory, a large part of whose goal is to explain what's going on and why this is happening. And it's full of conjectures, and not much is proved in this theory, but at least there's a beautiful effort at coherence of everything inside it. An attempt to really understand these connections that otherwise I would say they've just been showing up. Okay, so that's the plan of the talk. And everything is going to get less than a quarter of an hour. So my first challenge is to give you a quarter of an hour explanation of what Grothendieck-Teichmueller theory is really all about. So I have to be honest and say that even though in my head Grothendieck-Teichmueller theory is a profinite theory about profinite groups in geometry, that isn't exactly how it first began. Everything up there is kind of a references, so because I'll be mentioning objects and not quite defining them, and I'll be saying the braid group, and the definitions are actually up there, also anyone who wants can have the notes afterwards. That I'm not going to use these actually, but if I say the art and braid group, for instance, it's defined up there on the paper. The fundamental group of moduli spaces and so forth. Okay, so GT theory. It started by 2 different things coming together. One of these things was work by Drinfeld, and he was studying something called quasi-triangular quasi-Hopf algebras, which essentially are groupoids made with Bray groups. And he was studying how you could modify these groupoids made with Bray groups. And he came up with a group of possible modifications. And this was a pro-unipotent group. And he was able to write down the definition explicitly, which I will do in a minute. And at the same time, so he was really looking at Hopf algebras. At the same time, Grothendieck, so all of this was taking place maybe Grothendieck was taking place in the early 1980s and Rinfeld was doing this in the late 1980s. And he was thinking of something completely different, that seemed completely different. And what he was thinking of was study the absolute Galois group by its action on fundamental groups of Q varieties. Now this seems like a big order, but as he said, a pi1 of a variety can have a very simple structure, it can be free, that doesn't give much information, it can have a few relations. Then GQ goes into the outer automorphisms and you know something about GQ. And what he said was, especially moduli spaces of curves. Grothendieck had a great belief in the importance of moduli spaces of curves. He indicates all of this that I'm saying is written in this very vague, in this very poetic way that he has in Esquisse d'un Programme. So it's not like he's writing theorems, that he was describing his ideas. And he says, they contain everything anyway. These contain all the information about all curves, all varieties, all surfaces, vibrations over curves, everything. So these are what you should be studying. And he made two remarks, but he made these as remarks without giving any formulas or any proofs. And the two remarks he made were, one, if you want to find a group that looks like Galois, the Galois group has a property. It acts on all these fundamental groups. And it also respects maps between the moduli spaces, which are defined over Q, simple geometric maps between moduli spaces. Suppose you try to find a group of all automorphisms who have those properties. You can compute that group. That was the first remark he said. If you simply say, who are the automorphisms that act on these fundamental groups and respect the basic maps, you can actually answer the question. You can give the group. So, ought pi1 MGN, this is what I mean by this is a collection for all G and N, all together. And they're also linked by certain homomorphisms, which I'll tell you in a minute, is computable to, in fact, only dimension less than or equal to 2 counts. So what he's saying is if you can find the group of automorphisms of all of these groups which together respect all of the morphisms between them, well, you didn't need to bother with so many, because if you just took the dimension of the moduli space is 3G minus 3 plus N. And if you take this number equal to 1 or 2, so just 4 moduli spaces really, that's enough. You get the same group. From then on, the group will not change. It will extend automatically to all the others. And he says this is what he calls the Lego theory. Probably everybody's heard that word Lego because it's such a beautiful word. He put in all the topological spaces can be cut into little pieces. And in that way, the automorphisms from underneath, they propagate up to the whole moduli space and you don't need all this information. So all of this turned out to be completely right. And I want to just describe very quickly the maps that one takes between moduli spaces here. You have a surface of genus G with some marked points on it, and marked points. The moduli space is the moduli space of such curves with marked points. And on such a surface, you can put a simple closed loop, or a number of disjoint simple closed loops. And if you cut, what you get is, or you pinch the loop to 0, even better, you pinch this loop to 0. What you're doing when you pinch the loop to 0 is, on a topological space, you're making a node. But if you think of the analytic structure, if you think that this is a Riemann surface and it's a point on the moduli space, and you move the analytic structure to make this geodesic shorter and shorter, what you're doing is you're moving toward the boundary of moduli space. And when you compactify moduli space, you add these. These nodal curves are the ones you add to moduli space to compact it. At the same time, the space of curves with nodes like this is just the moduli space of these is MGN. The moduli space of this one is just the product of the moduli spaces of the two pieces, if I cut it in two with a loop like this. Sometimes a loop is not separating, and I just get one piece. And then the moduli space of these is just the moduli space of the cut piece. So MGN bar, this is the compactivation, equals MGN union boundary components obtained by cutting along simple closed loops. Maybe pinching. Pinching is probably a better word than cutting. You actually pinch it off and it comes apart. These are stable curves. You add them to the moduli space and it becomes compact. This is Deligne-Mumford compactification. So what you have here is you have a map from the moduli space of a piece to the boundary of the moduli space of the original curve itself. And this gives rise to a very simple map between the fundamental groups, which I can describe in an easy way. Just by telling you a very, very beautiful fact about the fundamental group of moduli space. The fundamental group of moduli space, which we call gamma GN, is equal to the mapping class group, which is just the diffeomorphisms of the topological surface of that type, mod the ones that are isotopic to the identity. Which makes sense, because if you take a Riemann surface and you consider it as a point on your moduli space, so a base point for the pi one, say, and then you slowly modify the analytic structure, it is like traveling around your moduli space. And if you then come back to where you were before with a diffeomorphism, you've made a loop on moduli space. So this really makes sense. And generators, some very special generators, are Dehn twists. So a Dehn twist is a diffeomorphism of a surface along a simple closed loop. So if this loop is called gamma, the Dehn twist will be tau gamma, is you just cut along the loop. Let's say you cut out a neighborhood of the loop like this. Your diffeomorphism that I'm about to describe is the identity here and the identity here. All you do is you take the middle and you just make one complete twist so that the two boundaries, it's the identity on the two boundaries, and then you glue them back. So really it's a local diffeomorphism right around the loop. You just twist around that loop and glue it all back. And that's a very important element in the mapping class group in terms of diffeomorphisms, but it's also a very important element in the mapping class group in terms of being the pi one. Because all it is this Dehn twist is a loop in the space MGN around the missing boundary component corresponding to gamma. Giving a loop, as I said over here, pinching a loop that corresponds to one boundary component that we add to the compactification, but it's not in the moduli space itself. It's like a hole, it's not there, and this is a little loop going around it. And now you can see in what I was saying here that even though you might think it's a bit strange for me to say, the smaller moduli space doesn't go to the bigger moduli space. It goes to the boundary of the bigger moduli space. Yet, this still gives a map between the mapping class groups. It may seem a little strange, but now this makes it very obvious, because if I take a Dehn twist here, which generates the whole thing, I just draw the same loop here, and I map it to the Dehn twist there. It's a very, very simple map. So what Grothendieck put on his tower is these maps. We call them subsurface inclusion. The subsurface inclusion maps are what I just described, because you cut along loops and you have a subsurface. And then point erasing. So you erase any point, any one of the marked points, and then you go down to the moduli space with one less marked point. These two maps. What Grothendieck says is compute the whole group of automorphisms of all of these respecting these morphisms between them. And you'll find that there's just a few properties describing the elements. And in fact, you don't need to use the higher Gn, but only the lower Gn. Now, somebody pointed out to Drinfeld, I can't remember who pointed it out to him. He mentions this in his article. He says, somebody pointed out to me that his group, GT, that he had described using Hopf algebras, acted very much like what Grothendieck was looking for. So now I'm going to just write down his group for you. The only difference, and the very, very important difference between Drinfeld's group and Grothendieck's group is that Drinfeld's group, it only cares about the moduli spaces in genus 0. So GT, this is the theorem really. This is the big theorem which, in Drinfeld's article, there's a page at the end where he says, somebody said to me that this could very well be the group that Grothendieck means because it acts on fundamental groups of moduli spaces. And then this was all completely proved. So it's the group, let me write, the group of all the pi 1 of n 0 n's respecting the maps, those maps, these maps that I've described, but only in genus 0. What does this mean? This is important. This means that you don't just take any automorphism of these groups, you take the ones that preserve inertia. Star means inertia groups, means conjugacy classes of inertia groups are preserved. The inertia elements are just these Dane twists. That's exactly what they are, these little loops around the missing boundary components. And any Galois action is going to preserve inertia, right? So if we're trying to find a group of automorphisms that has any relationship with a Galois action, it better preserve. This is like the most fundamental property of a Galois action. So GT does this. And it respects those maps, and it does everything. And furthermore, if you take just basically M05 alone, which is the dimension 2 moduli space, already it works. So Grothendieck was completely right. And I will just give you the formula for the definition of GT and the action on these, because it's very simple. So the definition of GT, let me give you the action first. First of all, we have to know that the pi 1 of M0n, so the mapping class group in genus 0, are really simple because they're really just braid groups. So these are very, very well understood groups. So pure Artin braid group, mod a very simple, the center and some simple element that goes away.
Wherever, you're talking about actual automorphisms in all these cases?
Actual automorphisms, yeah.
What do you know about base points and things like that?
Yeah, so, okay, so I should be careful. I could put outer automorphisms and I wouldn't have to mention base points. But you can lift them to actual automorphisms. And the base points that we systematically choose to do that are tangential base points near the boundary of moduli space. So there's a completely well-studied system. This whole theory of tangential base points is developed by Deligne. I showed you what the boundary of moduli space was. You take the strata, the minimal dimension strata, the zero-dimensional strata, that is, you put as many simple closed loops as you can on a surface and you pinch them all. And then you get a point, a very special point in the compactification of moduli space. And next to this point, you take a tiny neighborhood. And if you do that, it becomes simple, and it's exactly what I'm going to do actually. It becomes simple to write down, to lift this to automorphisms and write down what they do.
So you have a compatible collection of tangential base points and everything that
exactly. You have a compatible collection of tangential, especially in genus 0, it's particularly simple because I can tell you what they are. You draw kind of, okay. So let this be the equator of P1. So P1 is a sphere and this is the equator because I'm going to choose my tangential base points to be real just for simplicity. So what you do is let me pretend these 3 points are 0, 1, and infinity. So I'm looking at the equator like this. And you draw a tree. Actually, any trivalent tree that you choose will give you a possible tangential base point. The standard tree just looks like this. Okay, so you can choose this on all moduli space for all n, and you just keep erasing the last one to make them compatible with all of the n's. So what does this mean? I'm telling you that these points are the points of a maximally degenerate point. the more you branch, the closer they are to each other. So this is a bit of a digression, but let me just do a really simple one. Suppose I were just doing this one. That would tell me to take the sphere with marked points, minus epsilon plus epsilon 1 in infinity, where epsilon is kind of infinitesimally small. As far as I'm talking topologically, which is what I'm doing right now, it's just a little region parametrized by small epsilon. If I had another branch in my tree here, I would be taking minus epsilon squared, minus epsilon plus epsilon squared. And these would be even closer by a higher order of closeness than the others. Okay, so they're all crowding around the neighborhood of the most degenerate possible point. Okay, so the answer is, what you're saying is really only useful because, yes, I am going to want to write it down as an explicit automorphism. If I put out there in the theory, then I don't even need it. So what I'm going to do now is write the definition of GT very quickly. And for that, so this is generated by xij's, which are just braids, essentially, where the jth and the ith strand go around each other like this, which means here, what are my diffeomorphisms? It's just the endpoints on my sphere are moving around. That's all they can do. So when the endpoints are moving, this generating loop is just given by those 2 points traveling around, circling each other, and coming back. So GT is pairs lambda f in z hat star times the profinite completion of the free group on two generators, but really this is just pi1 of M04. M04 is P1 minus 3 points. This is the first moduli space. And then I have three properties which have become rather famous. So f is f of xy. And then I apply the automorphism changing x and y. And the product of the two has to be 1. So f of a kind of three-cycle relation, f of xy, z, x, y, z equals 1 when x, y, z equals 1. And then the famous pentagon relation. Now here, these x1, 2, 3, 4 that I'm writing, they're going to be all inside gamma 0, 5. So when I write f of x1 to x3, 4, I map my f. My f, in principle, is in the free group on two generators. I map it into gamma 0, 5 by x goes to this and y goes to that. That's the meaning of this term. And these just turn around cyclically. 1, 2, 3, 4. 1, 2, 3, 4. 5, 1. No, that's not right. 1, 2, 2, 3. 3, 4. 4, 5. 5, 1. 1, 2, 2, 3. 3, 4. 4, 5, 5, 1. Equals 1. This is something that lives inside the group here, inside the profinite group here. And what Drinfeld had written down before ever any connection was made with all this geometry of moduli spaces is that GT maps to aught of the profinite. Well, he was not working in profinite completions. He was completely unipotent, but the formula is the same. Sigma I, which is the base generator of the full braid group that just crosses the I and I plus first strands, maps to f of sigma I yi, sigma I to the lambda. So here yi is just sigma I minus 1 down to sigma 1, and then sigma 1 back to sigma I minus 1. He discovered that this gives an automorphism of the braid group in the pro-unipotent situation. But it wasn't that hard to prove that this still works in the profinite situation, that this gives a GT action that passes to the quotients gamma 0n, so the fundamental groups, and that action, and this is really the key point, does correspond to a Galois action for a certain choice of base point, which is a tangential base point, corresponding to the easy tree that I wrote down before. You could ask yourself, okay, GT acts on the fundamental group, but does that have anything to do with the Galois action? And the answer is yes, it is the Galois action. It's the Galois action lifted to an actual automorphisms by a certain choice of base point. And in fact, you can see this, because GT, this is a theorem, it's all of the automorphisms, just in genus 0, that have these properties that act on the pi1s of M0n this way, respecting those maps. And GQ are certain automorphisms that certainly do have those properties. So really, you can see right away that you have an injection like this. So that's Grothendieck-Teichmueller theory. And the big developments of this theory that it's had since then have been, is this an isomorphism? Any efforts to find more properties, to find properties of elements of GQ, are they satisfied by GT? Arithmetic properties of the GQ action, investigating whether GT has these properties. And the other direction has been higher genus. Because you can, and this has also been worked out a lot, not completely yet, but developing a GT for higher genus and comparing that to GQ. So Grothendieck-Teichmueller theory has taken these directions. But I'm not going to talk about them, because now what I want to talk about is the connections with multiple zeta values. So I'm going to go to part 2 and very quickly remind you what multiple zetas are, although I'm sure you've all heard this quite a bit. I'll change my transparency so that I don't have to copy down the definitions, if you can see this. Is it in focus? There. It's the top. Don't worry about the bottom. The top is the main definition. So it's this famous definition that just generalized basically the Riemann zeta function. Okay, so here, if you want this to converge, you better have k1 bigger than 1. The k1s are just positive integers other than that. And you have all of these values, and they're all real numbers. And they generate a vector space over Q. And the structure of this vector space is the whole study of multiple zeta value theory. First of all, you can easily show that if you multiply 2 of these, you get a sum of them. Just think of multiplying these 2 series, taking 2 series like this and multiply them, and you break it all up into the terms where some of the mi's might have been bigger than some of the ni's. Like here, I would multiply it by something like this. And then I have to take every different order where some ni's are bigger than some ni's, and I break it up into a big sum. And each of those is just a multiple zeta value. So by multiplying these series and then breaking up the product into ordered indices shows that this is an algebra. Let me call it. So this is Z equals a Q. So a priori, it's a Q vector space. But now we just made it into an algebra. So the first example you can do if you multiply zeta 2 times zeta 2 is you just multiply the 2 series and you break it up into the pieces where n1 is bigger than m1 in the other way, and you get 2 zeta 2. And then there's a term where the n1 would be equal to the m1. And that will give you a zeta 4. This is a special multiplication rule. You can write it down completely combinatorially. It's called Stuffle. It's said, we say that multi-zeta values satisfy Stuffle relations. These are these algebraic relations. They're always a product of 2 things equals a sum. And there are a bunch of algebraic relations satisfied by these. And then you have Shuffle. You have another way to multiply these values that gives you a different result. So in this case, just an example so that you can see that it's actually a different result. This is how you do it. And this is something very important because it suddenly links up to geometry. Everything I've written now about multiple zeta values, they look like nothing like the Galois group and nothing like geometry. And so the whole point of my talk is they really are containing information about all these things and why. So this comes from the fact that you can also write this as an integral. If you integrate, okay, so here's the integral, which gives exactly the same value as defined by the series up there, and there's no trick to it. You just keep integrating. You write k1 plus kr equals n. You have an n variable integral. You write epsilon 1, epsilon n is just a tuple of zeros and ones. So here, are k1 minus 1 zeros, k2 minus 1 zeros, up to kr minus 1 zeros. So you've got n things, the sum of this. And they're appearing here in your integral. And here I think you need a sign. And I gave the example up on the transparency there of the very first one, how you get zeta 2 this way. Zeta 2 is a little bit out of focus, but it's just 1 minus t2 over t1. The first example is this. So t2 is integrated from 0 to t1. T1 is integrated from 0 to 1. You just do the integral. Expand this out as a power series, do it. You immediately get n greater than 0, 1 over n squared. But something happens when you multiply two of these now. It's a completely different thing from what happens there. Here, when you multiply two of these, the whole differential form looks a bit like the same kind of differential form. But instead of having a simplex here, you have a product of two simplices. So you break that up into a sum of simplices. And you sum those. And that's what gives you the second rule. And it actually turns out to be very different. It's just two completely different multiplication rules. And each of them gives a set of algebraic relations on multiple zeta values. So the big conjecture on multiple zeta values is quite simply the structure of this algebra Z. That's what people are really seeking for. The structure of this algebra Z is conjecturally so there are two pieces to this. One is double shuffle. Double shuffle is the two, shuffle and stuffle, those algebraic relations. Double shuffle generate all algebraic relations between multi-zeta values. This is something which is really pretty astonishing, because why should they? There are loads of others that are known historically back from the time of Euler. People knew lots of them. But somehow it's felt also because of being able to verify computations in small rank that everything should really come from just this essential rule. And the other conjecture is much stronger, and it actually says Z is free. A free Q algebra generated by one element in each odd weight n greater than or equal to 3. The weight is k1 plus kr. Was it n? Well, it's gone. Oh, this is the weight. Every zeta value has a weight. So the weight should form a grading in particular. But that's not known. Nothing is known. Nothing at all is known about this multi-zeta algebra. Nothing will ever be known, not in our lifetimes, because we don't even know if they're transcendent. We don't know anything about them. We don't even know if they're rational. We don't know anything. It's zilch. So we can never prove any of these things. So what people do in order to explore the structure of Z and compare it with all these other objects is to pretend that it's okay. So the big principle is replace Z by Fz, which is formal zetas, which simply means that we take symbols that look like zetas and we make the assumption that one is true. We make the assumption that these are subject to double shuffle only and nothing else. So now we have an algebra that we can at least study. So with only double shuffle. Okay. If only we knew the structure even of this algebra. Now it doesn't seem so complicated, does it? We know exactly who the generators are. We know exactly who these algebraic relations are. We have no worries about transcendence. We ought to be able to prove this, no? But no, we have no idea how to prove this at this point. Maybe we're getting nearer to it. Maybe there's some progress being made. It doesn't seem out of reach, but at this point we don't know. Even with this assumption here, we don't know about the structure. But at least it doesn't seem hopeless. So now I can move to part 3 and really talk about the connections between.
Can I just ask possibly a very silly question? If the conjecture 2 is true, where does zeta of 2 fit? I mean, you think
Yes, yes,
that
it's
right
true.
now,
Tensor Q of zeta f2. It's true. I forgot. You have it's a very complicated structure that's supposed there. Let me write. I should have written it's Q of S2 tensor Q of S3, S5, S7, and so on. But these being non-commutative and that one commuting with the others, it plays a very different role. It's a bit special. This is actually the structure which is supposed. And the dimensions of the graded weight n parts of this are given by this is the generating series. If you expand it out as a series, this is the dimension of the weight n part of that. And it's given by a recursive formula. This just shows it in fact. To give this is the same as to give it recursively like this. And you say D1 equals, D0 equals 1. That's Q. You've got a Q in this Q algebra. So the weight 0 part is Q. D1 is 0 because we have no weight 1 zeta because zeta of 1 isn't there. So you take zeta of 1 to be 0. Just forget it. D2 equals 1. This is zeta of 2. Then from then on you have them all by this formula. So D3 is going to be equal to 1. And you see that it really is going to be generated by S3. And in the real numbers, insofar as we can calculate with them, there is only zeta 3 and nothing else. And then it grows. And in small weight, the kind of people who work with real numbers to sufficient number of decimals and prove in this way that they must be transcendent because you can't have an algebraic relation, have proved that these dimensions really do correspond to real zeta values up to some small weight like 12. So thanks, because I forgot about zeta 2. Okay, so now I'm on to 3. Connections. Now, the problem with these connections is that I've described to you an algebra. Now, this algebra, one nice way to look at it is the enveloping algebra of a co-Lie algebra, which is what happens when you just quotient any Hopf algebra mod products. Z, we don't know if it's a Hopf algebra. We don't know anything about it. But for FZ, we do. FZ has been shown to be a Hopf algebra by Goncharov. Goncharov put a coproduct on it, which is very complicated, but very pretty. And he showed that this is really a Hopf algebra, and you can quotient it by products to get a Lie coalgebra. So if I write F here, I'm not risking anything. So we're in the world of Hopf algebras now. We're in the world of Hopf algebras and Lie coalgebras and their duals, which are Lie algebras. But GT is a profinite group. And it's out there in the world of Galois actions on fundamental groups. So how can we compare these two things? So we can't. The answer is we can't, because GT, GQ, they contain infinitely more than multi-zetas ever will. You have to come down. You have to take your GT and come down to the world of Hopf algebras and Lie algebras if you want to compare. So take GT down to Hopf Lie algebra world. Now, this isn't as ridiculous as it sounds. That's where it came from. Drinfeld first defined this group as a Hopf algebra. Anyway, in the context of Hopf algebras, he defined it as a pro-unipotent group, which is the exponent of a Lie algebra. So this really is where it originally came from. So it's not so strange. But it seems like a strange thing to do when you're thinking in terms of Galois actions. However, it actually works very well even in terms of Galois actions, which will be which will be part 4. So for part 3, I just want to talk about GT, and then for part 4, I'll tell you what happens when you do this to GQ. So to take a GT down to this world, you just make a Lie algebra of GT, a graded Lie algebra. So the graded Lie algebra, the first thing that happens is that this lambda, which corresponds really to the cyclotomic character of GQ, disappears. Now in the world of Lie algebras, it's gone. So here you have elements which are just Lie polynomials in 2 variables instead of being in the free group on 2 generators. We had the free profinite group on 2 generators. Now it's the free Lie algebra on 2 generators. And they satisfy these three relations, which we already saw, but now they're just additive. And there's no lambda anymore. So you can see, on the one hand, that this Lie algebra of GT just completely reflects the structure of GT. And on the other hand, that it's also simpler. So here you have these same 5 terms. And the xij no longer live inside the gamma 05 fundamental group of moduli space, but inside the Lie of the 5-strand pure braid group.
Sorry, so Drinfeld's Grothendieck-Teichmueller group was also probably not a pro-unipotent group.
Drinfeld's Grothendieck-Teichmueller was a pro-unipotent group. It was a K pro-unipotent group.
We didn't have a GM component for this?
No.
Really?
No. He didn't have a GM component. It's interesting that you asked that, because you're thinking of... To say something is graded is essentially the same as saying that there's a GM acting on it.
Well, that's true. But
So essentially the GM is reflected in the fact that this is a graded algebra.
so in his definition, there was no lambda in it?
He didn't define this. Yes, there was a lambda. No. The lambda and the GM component are not the same thing. So yeah, he defined it with lambda. But when you know, that's really an interesting question. Lambda goes away when you come down to the Lie algebra.
Is lambda also plus minus 1?
No, that's not true. No, not if you're working over a field K and you have K point and point. That's true if you try to take a discrete GT. But no, the GM component in the sense that you're thinking of really has to do with the fact that this is graded and it's there, whereas the lambda, the fact that there isn't any lambda in the Lie algebra situation for a reason which escapes me right now. I can't remember. It's probably something that I understood many years ago, but it just disappears from the definition. Let me say just why I think it disappears from the definition. Because it appears only in the one relation anyway, which is this one. And when you make this additive, yeah, it literally disappears. Because these three, okay, this was the multiplicative definition. Lambda didn't even appear in the definition of relations 1 and 3 in the profinite case, only relation 2. And it was like this. And when you make this one additive, the x plus y plus z is 0. So this one actually, just the lambda cancels away when you make this additive.
Sorry, I don't want to distract you so much, but if you're thinking in terms of pi 1, one way of thinking about it is that if you look at only those automorphisms that act trivially on homology, then you'll get something of this nature. The lambda will go away.
But of course, if you're thinking it in even in Galois terms, it's like just taking elements with a cyclotomic character equal to 1. So essentially, that's exactly what it is. It's not that it just acts, it's not that it just conjugates the cyclic groups of inertia. It conjugates the inertia elements, actually. But here, when you're acting as derivations on the Lie algebra, you don't multiply them by a constant. I don't know exactly why. Somehow, this is the algebra that comes out when you simply linearize the definition. Okay, anyway, this one has some very, very nice properties, and I would say various things that I meant to say about it, which I'm now distracted from. Okay. The first thing I want to say is this EDZ that I took before. Formal multiple zetas mod products. This is a Lie coalgebra, which is what happens when you mod a Hopf algebra mod products. So the dual is a Lie algebra. And this dual has been well calculated. And the dual is something that we're going to be able to much more compare to this GRT here, because GRT is a Lie algebra, and it's contained in Lie of xy. DS is a Lie algebra, and it's also contained in Lie of xy. So the natural comparison here is not between GRT and formal zetas, but GRT and the dual of formal zetas. So this is given by Lie polynomials with a certain property, which is quite simply that a certain you take the elements that a certain coproduct acts nicely on. So here, f star is equal to, let me just assume that f is homogeneous of degree n. I just take a generated by the homogeneous polynomials. Then f star is equal to this. I take the coefficient of one particular monomial, multiply it by y to the n, and I added it to pi y of f, which is just take only the terms of f that end in y. So f is a Lie polynomial, but you can also expand it out as a polynomial. Some of the words end in x, some of the words end in y. It's free, so there's no ambiguity, and I take only the words ending in y, and not the words ending in x. And if I do this, I see that every word in f star ends in y. And that means that f star can be written as a polynomial in yi's, which are x to the I minus 1 y. And then I define delta star on these yi's by the sum over k plus l equals I, yk, tensor yl. So this is a coproduct on q of the yi's, on a smaller space than q of xy. So I have this coproduct acting on this element, and I have to have that. So I take all f's with this property. This is double shuffle, because already the property of being Lie is the dual of the shuffle multiplication. And this is exactly the dual property to the stuffle multiplication. So it's exactly the two shuffle relations which are the dual of what we saw for formal zetas. But it's much easier to compare these two because they both live inside the Lie algebra of xy. But why do we compare them? What is the reason to compare them? What would make us even think they can be compared? And the answer is one word. This, I think, is the key thing discovered by Drinfeld that shows why there's a connection between these different theories. And the key word is the Drinfeld associator. The Drinfeld discovered, so Drinfeld took a Knizhnik-Zamolodchikov differential equation. He studied solutions of this differential equation. He took two solutions, this one tending towards z to the x as z tends towards 0. Z to the x is a power series in z and x. Exp to the exp of x log z, the power series in x and z. He took another solution that looks like 1 minus zy as z tends towards 1. He took the quotient of the two solutions. Now, the quotient of any two solutions of this is just going to be a constant. When I say a constant, I'm talking about the field of power series in x and y, non-commutative variables x and y. So this is a constant. And this element is the Drinfeld associator. And what Drinfeld showed is that the Drinfeld associator satisfies relations, satisfies GT type relations 1, 2, and 3. So they're almost exactly like these relations except multiplicative. I wanted to say something that I forgot to mention because I don't really need it, but it's a beautiful theorem by Furusho, who proved recently that you don't need those three relations because 3 implies 1 and 2. So you can cross them out, and you just keep relation. The pentagon relation only defines it. That's a very, very nice result. We tried very hard to prove that for the profinite group, and we really couldn't do it. It seems like almost like it's not true for the profinite group, so it may be a key difference between the Lie algebra and the profinite group. Anyway, I think it was Wojtkowiak who noticed something really interesting about this Drinfeld associator, which is that its coefficients are multiple zeta values. In fact, it's just given by zeta. So W is just all words in x and y. And zeta, if a word W begins with x and ends with y, so if W is equal to x to the k minus 1 y, x to the kr minus 1 y, which is just saying that it starts with x and ends with y, then zeta of W is equal to, I should write a star here maybe, is equal to the ordinary zeta value of k1, kr. If W doesn't start in X and end in Y, you can calculate this, and it's a linear combination of the ones who do. But explicitly written out also by Jussieu. I mean, other people discovered you could do it, and he wrote out the explicit formula. So all of these are either the multi-zeta values that we know or linear combinations of them. And so they satisfy double shuffle. So these satisfy double shuffle. So we have this element which you can really consider as being in, just for convenience, because I prefer to work in Lie algebras rather than Hopf algebras, I'm going to consider them reduced mode products. So I can write that this is an FZ tensor. If I do that, what Jussieu showed is that if I do that, instead of satisfying the multiplicative relations, they end up satisfying exactly those relations. And then in fact, this phi kz reduced mod products, it ends up being in this tensor product really. But when you have an element in a tensor product, what you can interpret as just being a map from Gert to the dual of FC, which is just this double shuffle that I defined over here for you, the dual of FZ. So it's just this double shuffle. So what are we saying now? We're saying we have a map from GRT, which is in Lie of XY, to double shuffle, which is in Lie of XY. So that's something that maybe we can see what this map is. Except that nobody could see what this map is directly by looking at this. Because I cheated here. This is not true if I write formal zetas here. It's actually, to be honest, only true if I write NZ here.
Could you explain that equation again? What did you say? F pi kz equals?
Here, in. Sorry. It lives in here with coefficients that are not in Q, with coefficients that are zeta values. So it's in the tensor product of zeta values with this.
How are you viewing it that way? I didn't really know.
Well, originally up here, you could say that it's just in Z tensor. And here you have to have a Hopf algebra associated to GRT, the universal enveloping algebra here. Because what are the elements of this? They're elements that satisfy these relations but whose coefficients are in Q. Now my coefficients are in Z. So it lives inside here. Now when I reduce the coefficients mod products, which is really just for simplicity, I end up inside here. And this comes down to be the Lie algebra also. Okay, so I have a map like this. But okay, I'm unfortunate because we don't know anything about this. This is real zeta values. We don't know that the dual lives in Lie of XY. We don't know anything. So I really wish I could replace this n by the formal ones. But if I do, of course I believe I can because I believe they're the same. But if I do that, I don't have this property anymore. Nobody knows that if I replace the real zeta values by the formal, nobody knows that we satisfy 1, 2, and 3 anymore. So we no longer can write this with F. So we don't have a map. So what I'm saying is by analogy, by conjecture, we suppose that we could do that and that we would get a map like this. But we can't use this reasoning to say that we have it. However, if you just pretend you have it and you look at what it could be, you see an amazing thing, which is that we do have a map like this. We don't know if it comes yet from this reasoning. It should morally, but we don't know. We just see the map. It seemed from calculation in small weight that the map was just this. Anytime you took a literal actual Lie polynomial satisfying those properties and you put fx minus y, it then satisfied these properties. And this is an observation. Just people were calculating what this looks like in small weight. And they were calculating what that looks like in small weight. They had the same algebra. So this was really surprising. So the feeling was, we do have, it looks like we have a map. In small weight this works. It can't be a coincidence. These polynomials are very strange. It's not like lots of polynomials satisfy that. There are very few. And they're the same ones that are coming up here. Why? Why would we have this map? And do we even have this map? Or is there something happening in small weight? And the answer is, we do have this map. This is an injective map. This was proved very recently by Jussieu. And this is a beautiful proof which uses a double polylogarithms and the fact that he managed to figure out double polylogarithms satisfy very double shuffle looking relations, but in the Lie algebra of the Bray group. And in order to push those relations down to the normal double shuffle, he uses the pentagon. It would be great if he could find a converse of this result, because we really conjecture that they are isomorphic, and we conjecture that the isomorphism comes from a formal Drinfeld associator. But this is a very strong piece of evidence confirming what we believe, which is there really is a formal Drinfeld associator which works, but we don't know it yet. So what I just described to you is the strongest piece of evidence we have about a relation between Grothendieck-Teichmueller theory and multiple zeta theory. But two things are missing from it that make you really wonder. One of them is, where's the geometry of moduli spaces in here? And the other is, where is the Galois group? So since I don't have much time left, I'm going to answer the first question in one sentence that will just tell you how much more stuff there is to do. So two things missing. This shows that we have a big connection between GT and multiple zetas, right? This map right there. It's not just an injection. This injection is practically the identity. But if we think of Grothendieck-Teichmueller theory in all of its power, we've got a Galois action on a fundamental group. Well, I'm leaving out the word. Fundamental group of moduli spaces. These two things, they're missing from this description here. We just have this GRT, which I wrote down. The definition looks like GT, but you can't see any more of the interesting geometry. So I'm just going to say one word about this and a couple of words about that. So for this one, the answer is multiple zeta values are periods of moduli space. And that's very easy to see because I showed you how to get them as an integral. I integrated over a simplex. I integrated a certain form. But that simplex, you can just as well see it as living in the moduli space. And those T1, Tn, they could be marked points on a sphere. So I did actually get them by integrating over a simplex in moduli space. But conversely, all periods of genus 0. We're profoundly in genus 0 with the whole theory. All periods are linear combinations of MZVs. This was quite a big theorem by Francis Brown that's fairly recent. So when we're looking at multiple zeta values, we're looking at the periods of moduli space, and without really openly saying it, we're looking at the cohomology of moduli space, and there's a very large theory developed about this, which I don't have time to say even a single word about. But it's emerging that the geometry of moduli spaces and the multiple zeta values are very much related, and this is the key point of their relation. And now about the Galois, well, we had an absolute Galois group. Well, you saw what I did to GT. I took this huge profinite group that was acting on all these fundamental groups, and I made it into that little Lie algebra, which is really quite a small Lie algebra, which looks very much like it's generated by one element in every odd rank. Can I do something like that to GQ? I can. This is what Denini and Ihara understood. They understood that you can take GQ and make a little Lie algebra out of it. And okay, admittedly, you're going to lose a lot of interesting structure of GQ, right? But you can see exactly what remains. There is arithmetic that remains here, and it's completely understood. So this is what they did. They took F2, just seeing this as the pi1 of P1 minus 3 points. For a reason of working over a field, we take the pro-L completion rather than the profinite completion. You mod it out by all the groups of the descending central series, so the commutator and commutators of commutators and so forth. And you take the kernel. So this is equal to kernel of that map. And there, by doing this, as the groups you're modding out by get smaller and smaller, the quotient is bigger and bigger, the kernel gets smaller and smaller, and you filter GQ. So we have a filtration. So the first group in this filtration, it occurs, well, the first is 0. So this is just F2 mod F2. It's 1, so it's everything. It's just GQ. And the second group in the filtration occurs when you mod out by the commutators. And you get an abelian group, and so all that remains is the cyclotomic action. But since we're working over QL here, it's just GQ mu L infinity. And then they get smaller and smaller and more complicated, and we don't know. But what they showed was that the successive quotients are abelian. They're actually ZL modules. They're abelian, they're ZL modules, and so they tensor with QL to make a Lie algebra. This is a Lie algebra, which I call the Deligny-Haar algebra over L. It has a Lie bracket that is very simple. The Lie bracket just comes from lifting two elements and just taking the commutator upstairs in the Galois group and then putting that back down again. That's what makes the Lie bracket. So they have this Lie algebra. And because GQ injects into GT, which we saw earlier at the profinite level, you can deduce that this injects into this as long as you make sure to tensor it with QL, which is a little bit disappointing, but there's no way to construct this one directly over Q. But Furusho's theorem that I just talked about showed that this goes into double shuffle tensored with QL. This injects into double shuffle tensored with QL, which is what double shuffle is. It's the formal multi-zeta dual. So my last word is going to be, we can forget the middle thing and we'll take the dual of this map. And the dual of this one gives us that formal multi-zetas surject to the dual of this. The dual of this is very well understood. If anything, the dual of this is better understood than the thing itself. And I'm going to tell you exactly what happens here. The first question anybody asks when they say, but the multi-zetas go somewhere, is where does this go? Zeta n for n odd. These are the key elements, really. And I will tell you where they go. They go to the Soule characters, which are characters from here to ZL. If I have a character that goes from here, then I can certainly take it down to the DI, because DI is all successive quotients of this. And I'm just going to write it down for you so that you can see exactly how, this kind of gives you the information of exactly how much Galois theory remains when you do this procedure. So chi of n, okay, so you have sigma of a to the 1 over ln. So you take an L to the nth root of a certain a, which I'll write down. And the Galois action has to multiply it by a root of unity and fix a primitive root of unity. And this is where the Soule character occurs. And I just have to tell you who A is, what field we're actually working in here. So L doesn't divide A. You take the product over all A of 1 minus a primitive root to the A to the A. Okay? So what are we really saying here? We're saying some Galois theory is left when you take the whole absolute Galois group and you bring it down to this DI. It's the Galois theory of this field, of these fields for varying primes. And these elements correspond to the multiple zeta values. And this is kind of the heart of the matter. This is really the subject of my talk, basically. What is the connection between the GQ, the GT, and the multiple zeta values? And the answer is, it's this. And we know the answer. We may not understand completely what all this means. There's still really something to understand here, but these things are proved. This map here is entirely proved. And the dual surjections, this is proved. And this really exists. This is what happens. Of course, we conjecture that this is an isomorphism. We conjecture that both sides are free with one generator and all that reg. We conjecture much more about the structure. But this is not conjectured. This is proved. So I guess that finishes it. I think I gave you as many connections as I could think of.
What does it tell you? And is this an isomorphism? So one expects that this is an isomorphism?
One expects that this is an isomorphism. Was that your question?
So, and what does it say if, suppose that the formal zeta equals the zeta, what?
No, that says that zetas are all transcendent, so that we know everything about zeta values and their transcendence. That says much too much. If you like mixed tape motives, I can say that all of these conjectures can be reformulated by saying that the category of mixed tape motives and ramified over Z is the same as the subcategory you get inside it by just taking motives coming from the motivic Galois group of P1 minus 3 points. It's sub-objects and tensor products and quotients of that. That's a subcategory. And if that's the whole category, if those are all mixed tape motives, then that's, again, the same question. Then you have a further subcategory of mixed tape motives, which is multiple zeta motives developed by Goncharov. So there are 3 objects. And it's like saying the category of mixed tape motives, the subcategory of just the ones coming from P1 minus 3 points, or moduli spaces, and the one of multiple zeta values. These 3 categories would all be the same. That's the part of it I didn't actually talk about. What's nice about it is that all these objects come up just from being subcategories of mixed tape motives, so they all come up in the same way. It's a rather harmonious presentation of what's going on.
Would this be the same without formal zeta equals zeta?
You know, it's an amazing thing, but in this theory, you could just forget the real zetas, basically. For most practical purposes, you can just forget about them because,
The true zetas.
yeah, because you can't work with them anyway. Until you tell me what zeta 5 really is. It seems like we would really be closer to proving any of the other results that are here, any of the other conjectures than that one.
The GRT, that this inclusion is an isomorphism, would also has nothing to do with that. I don't. You said something somewhere that if you know that these are equal, then something. Before you mentioned the theorem of Furusha.
Was it the formal associator? We don't know if it's an associator. Yeah, that's very annoying. We know that real zeta values satisfy a bunch of algebraic relations coming from 1, 2, and 3, coming from associator relations. But what we don't know is whether those come from double shuffle. It's the same question. See, people conjecture that double shuffle are all algebraic relations, but at the same time, they can give loads of other algebraic relations, like the ones coming from relations 1, 2, and 3 of the associator. And you're conjecturing they come from double shuffle, but you don't know. So it's really the same question. If all algebraic relations, if the associated relations come from double shuffle, then you can do what I said. But if Furusha can manage to prove the converse of his theorem, then we'll know that it's true, or that will prove it. And he doesn't use methods that have anything to do with the associator. He actually uses other methods. He uses polylogarithms, and he uses things that are very, very astute.
You say that the converse of Furusha's would mean that
If GRT and D double shuffle are isomorphic, then to satisfy the relations 1, 2, and 3 would be the same as double shuffle and vice versa. These would be the same ideals of algebraic relations. Whereas as of now, we only know that one is inside the other.